Good morning, one and all. So, in the last class, we have seen one more type of modulation, that is delta modulation. As I told you, it is a 1-bit version of DPCM. In the DPCM, if you replace a quantizer with 1-bit quantizer and the predictor with a first order predictor or simply a delay element, you will get a delta modulation. So, we call it the delta for the best known reasons. Why? So, in the staircase waveform, it may either increase by delta or decrease by delta anyway. So, this is the error and this is the output of the quantizer. If the error is positive, the output will be plus delta. If error is negative, output will be minus delta, output of the quantizer. Okay. Now, so this is about B of n, output of the quantizer. Now, since it is 1-bit quantizer, B is only 1 bit to transmit, either 1 or 0. So, generally what we do, we assign 1 for plus delta, 0 for minus delta. Okay. Now, these are all some terminologies from the diagram. So, these are simple things. Now, what happens here? So, finally, U of n will become U of n minus 1 plus delta. What is U of n? U of n is so input to the delay element. Okay, this is what U of n. Okay. Now, so what is U of n will be U of n minus 1 plus delta. So, when it happens, when the error is positive, U of n equal to U of n minus 1 plus delta. So, when the error is negative, U of n equal to U of n minus 1 minus delta. So, there is a increment by delta. Here there is a decrement by delta. So, why there is increment and why there is a decrement? It depends upon the sign of the error. Okay. So, correspondingly we transmit 1 or 0. So, this is the reason why we call it as a delta modulation, and obviously the output quality will be moderate. It is not that accurate. So, this is a problem here. You don't follow this. So, this is the simple waveform for the delta modulation. So, this is the continuous time waveform and this is the staircase approximation. So, you can clearly see here. So, either you may get increment by delta or decrement by delta. Delta will be constant here. Okay. So, this is the delta modulator which tries to follow the given continuous time signal in the staircase form. Okay. Next. So, this is a receiver. So, we do exactly reverse in the receiver. So, in the transmitter, what you have done? We have done addition, right? So, if you go back, so we have done addition. Sorry, we have done subtraction. So, here we will do addition. So, this is about delta modulation, and in the delta modulation there are two problems as I told you in the last class: slope overload distortion and granular noise. So, when the slope overload will occur? When the slope of the input analog signal is more than the slope of the staircase. The simple reason is, so when you get the slope overload distortion or slope overload noise, whenever the slope of the given continuous time signal is more than the slope of the staircase. So, then you get the slope overload distortion. So, when you get this granular noise, reverse. Whenever the slope of the staircase is more than the slope of the given analog signal. Okay. So, I am talking about local slope. So, here, so at this point, at this region, so the slope of the given analog signal is more compared to the slope of the staircase. Here also. So, the slope of the analog signal is more than the slope of the staircase. Okay. So, here it is rising sharply and it is falling sharply. But, so the staircase is unable to rise fastly as well as fall fastly. Okay. So, there is a mismatch. That is called slope overload distortion. The reason is the slope of the staircase is less than the slope of the given analog signal. Here, so when you get the granular noise, the slope of the staircase is more than the slope of the given analog signal. So, in other words, whenever the slope whenever the given signal is flat. Whenever the given signal is flat, so you may get some oscillations around plus or minus delta of the staircase. So that is called a granular noise. So generally this occurs whenever input signal is having flat like curve, or whenever it is having some small variations. Whenever the input analog signal is something like flat curve, or whenever it has some small variations, you may get this slope overload distortion. Okay, so this is simply granular noise. This is the slope overload distortion. So obviously, what is the remedy? As I told you, so the reason is here the slope of the analog signal is more than the slope of the staircase. So we have to increase the slope of the staircase. What is slope of the staircase? As I told in the last class, delta by Ts. So how to increase the slope of the staircase? By increasing delta, isn't it? So that's why to overcome this slope overload distortion, we increase delta. We cannot change the Ts. It is related to the sampling period. So here, what is the reason here? The slope of the staircase is more than slope of the given analog signal. So we have decreased the slope of the staircase. How to decrease? By decreasing delta. So that's why the remedy for the slope overload is increasing delta. The remedy for granular noise is decreasing delta. So they are contradicting each other. Okay. So anyway, we cannot remove both at a time, because in this delta is constant. Okay. So that's why you can remove any one. You cannot remove both. So that is a problem of delta modulation. So I have taken simple example of sine wave. So what happens if the slope is equal, if the slope is more, if the slope is less? So you go through this example now. So there is one more advanced version of delta modulation, updated version, that is called adaptive delta modulation. So your name itself indicates it is adaptive. What is adaptive? The step size is adaptive. Here the step size is not a constant now. So we can change according to our need or our requirement. Here, so this logic will decide the step size of the quantizer. Okay, so we have extra term, extra device, that is called logic for step size control. So what happens now here? So whenever there is increment, so here you can see very clearly. So the step size is increasing. Here step size is, this is the step size here. Here the step size is more than the previous step size. Here it is even more. Okay, so by doing so, we can able to overcome the, so somebody is following. Still there are some problems will be there, but anyway, so this is the continuous time signal and this is the staircase approximation. They are somewhat following. Okay, and so whenever the curve is somewhat flat, so there are no oscillations of the quantizer around plus or minus delta. Okay, so by adapting to the local slope, we can eliminate both the problems to maximum extent. Okay, so this is where you can get. So here the step size is delta 2, here delta 1. Delta 2 is more than delta 1. It is increasing. It is not constant throughout the curve. It is increasing. It is more. Here it is even more. Something like that. Okay. So that is briefly about delta modulation. So next, so let us go to another topic, that is called time division multiplexing. So in the unit 1, so we have seen frequency division multiplexing. So there itself I have mentioned about time division multiplexing. So multiplexing is two types: frequency division, time division, and wavelength division. In time division also there are two types. Okay, what are they? Synchronous, asynchronous, all those things. So these are simple theoretical thing. So by defining time division multiplexing, what we do? So we transmit multiple signals at different times. Okay, what do we do? So transmitted one after another through the same channel, we transmit more number of signal one after another. Okay, that is called time division multiplexing. Here what happens? There is a division in time. Time is divided among the users. Okay, and the sharing of the channel will be based upon the time. So sharing of the channel is done on the basis of frequency. Where? In FDM. In the frequency division multiplexing, the sharing of the channel is done on the basis of frequency. We have seen already. But here in in time division multiplexing, the sharing will be done based on the time. Time will be shared among the given multiple users. Okay. Now this is very, very important. So you note down this point. So in frequency division multiplexing, all the signals of different frequencies are transmitted simultaneously. Okay, that is called composite signal. But here in time division multiplexing, all signals are operate with the same frequency, are transmitted at different times. Okay. So in FDM, so signals occupying different frequencies are transmitted simultaneously. But here, signals having same frequencies will be transmitted one after another or at different times. Okay. So that is simple difference between frequency division multiplexing and time division multiplexing. Okay. So these are some theoretical things. Please go through them once. So this simple diagram which tells us about time division multiplexing. So we have multiple number of users to be transmitted or signals to be transmitted. We are doing multiplexing. We transmit over a channel. Next we do demultiplexing, and finally we receive the all different multiple signals. So this is also very, very important point. You may note down this point. So generally, time division multiplexing is more suitable for digital signal multiplexing, or in the digital communication we use time division multiplexing. Okay. So generally we use frequency division multiplexing in analog communication, time division multiplexing in digital communication, because it is most suited. Why it is suited, we will see later. Okay. Now, so here, so this is also very, very important. So please look at this. Now this is what we do for the time division multiplexing. Okay. So here, so at this here we have multiple number of signals that need to be transmitted. So we are using a low pass filter to eliminate some unwanted frequencies. Now here we have something called commutator. It's called commutator. So what the job of the commutator is? It will select sample from each and every signal. What it will do? It will select a sample from each and every signal. I will take an example, and we do modulation and we transmit over a channel. We do demodulation, and this is decommutator. So these two will be asked to be synchronized. Okay. Next, so we do again low pass filter reconstruction. Sampling, it is something like sampling and reconstruction here, and we will get the output message at the receiver side. Now, so this commutator and decommutator need to operate synchronously. Okay. So they should operate coherently. Why? So we will see with an example. Okay. So commutator and decommutator are two important components of the time division multiplexing. So they will simply collect the samples. Okay. So this commutator will collect the samples of the given multiple signals which are to be transmitted. Okay. It will collect and it will decollect, or it will distribute. Okay. We will see with an example. So this is simple time division multiplexing scenario. So here we have 4 users. They want to transmit over a same channel but at different times. So this is called multiplexing and demultiplexing, or demux. Okay. Now here what we do? First user, second user, third user, fourth user. First user has got 2 symbols to be transmitted. Second user also has got 2 symbols to be transmitted, so on, so on. So each and every user has got 2 symbols to be transmitted. Now, so what we do here is, for each and every user we allot a time slot. What we do? So for each and every user we will get a time slot, a unique time slot. Okay. So what we do first? So first in the first time time slot is given to the user 1. So he will transmit. Okay. What will transmit is first symbol A. Next, so the next time slot is given to the user 2. He will transmit his symbol B. Next, so third time slot is given to the user 3. He will transmit his symbol C. Next, D. So we got a symbol from each and every user. Now again we repeat the same thing. Next, A from user 1. Next, B from user 2, so on, so on. So this is called a frame. So in a frame there are 4 time slots. So it is called a frame. Okay. So here what is happening here is, so frame contains 4 time slots. So they belong to 4 different users. So this is called a frame. Okay. Now next we do demultiplexing. What do we do? So we take this symbol, we keep it here. Next symbol here. Next symbol here. Next symbol here. Again, this keep it here. This keep it here. This keep it here. Finally, keep this here. Okay. So like this, we can transmit multiple number of signals using same channel by sharing the time among the users. What are we doing? We are allocating a time slot to each and every user. So they have to transmit during that time slot only. Okay. So each and every user will be given a particular time slot during which they have to transmit their symbols or their information. So please go through it once. I have given the PPTs now. So I have taken a simple example. So I have taken 3 signals. I have taken their samples, not the continuous time signals. I have taken their samples. So this is the first signal, second signal, third signal. Now, so here I am taking samples. So let me go back to this diagram. Here, as I told you, this commutator will collect the samples. Okay. Now here, so these are the signals that are need to be transmitted. Okay. Now, so here we have to transmit 3 signals using same channel by sharing the time or by dividing the time. What we'll do here is, first we transmit these 3 samples. What are they? The first samples of all 3 signals. The first sample of first signal, the first sample of second signal, the first sample of third signal. We transmit them first. Okay. Next, during next frame, we transmit the second samples. So the commutator will collect the second samples from all 3 signals. Next, so one cycle will be over, no? So what we will do means, it has some cycle. It rotates like this. So if it completes one cycle means it collects first sample from all 3 signals in one cycle. Next cycle it will collect the second sample from all 3 signals. In the third cycle it will collect third samples from all 3 signals. Okay, so on. Now this is what the time division multiplexer signal. So if you observe very carefully, so these 3 samples are they belong to they are simply the first samples of all 3 signals. Okay. So blue, red, green. So they are called, this is called a frame. It contains first sample from all 3 signals. Next, so these 3 are second sample from all 3 signals. So on. Finally, these 3 are last sample from all 3 signals. So this is 6, value is 6, your value is around maybe 1, this is around minus 5 or 4, something like that, 4. So like this is called time division multiplexing. I have shown only TDM, multiplexing only. So this is the job of the commutator. So it makes a cycle. So it will, by the time it completes a cycle, it will collect one sample from each and every signal. Okay, they will be modulated, they will be transmitted, and it will do distribution. So decommutator will do reverse of the commutator. Okay, so they will rotate like this. They have rotation, something like this. So they will rotate. So by the time they complete a rotation, so they will collect a sample from each and every signal. I mean multiple number of signal that need to be transmitted. Okay. Now, so let me take one more example. So this is, I want to transmit 2 signals. One is sine wave, other one is triangular wave, with the frequencies given like that. And this is sampling frequency omega s, that is 13 times of omega m. So this is a sine wave, this is a triangular wave. I wish to transmit using same channel but at different times. or using time division multiplexing. So first what I do, I will do sampling. This is sampling of sine wave, this is sampling of triangle wave. Now what we do? First, so I will take first sample of first signal and first sample of second signal. So these two samples belongs to the both signals. They are first samples of both signals. Now these two are the second samples of both signal. So on so on. Now you can observe very carefully here. So this is called multiplexing, time division multiplexing. Okay. Now if you join them just like this, these are the samples of triangular wave, correct? Now these are the samples of sine wave, isn't it? Okay. So but you are transmitted using time division. Okay. So this will be done by commutator and so reverse will be done by decommutator. Okay. Now this finally TDM signal. So these two samples are first samples of the both signals, and these two are second samples of the both signal, so on. These two are last samples of the given both signals. Okay, and this is a reconstruction or recovery. So this is what is being transmitted. These two are transmitted using TDM, and these two are received at the receiver, and so almost they are similar. Okay. Now, so as I told you, digital multiplexing is TDM, and it is two types: time division synchronous and asynchronous TDM. Okay. So what do you mean by that? What do you mean by synchronous asynchronous TDM? Now here, so let us take this simple example. So here we have 4 users. How many? 4 users. So they want to transmit their data. Okay. Now, but so here user 1 has got 2 alphabets or 2 letters. User 2 has got 1. User 3 has got 1. User 4 has got 2. Now, so here, so in the synchronous TDM, I told you this already. So this is synchronous TDM actually. Okay. Here what happens here is, so here we allocate a time slot to each and every user, whether the user has something to transmit or not, whether the user has any information to transmit or not, we don't bother. We simply allocate a time slot to each and every user. We allocate a particular time slot to each and every user, whether he has something to transmit or not. Okay. Now here, so let us take this example. So here, what is happening? This user 1 is allocated a time slot, is transmitting A, first symbol. Next, user B, user 2 transmitting symbol B, user C transmitting symbol C, user 4 transmitting symbol D. So this is called a frame. Here in the frame there are 4 time slots. Generally in synchronous TDM, so the number of time slots in a frame is equal to the number of users. Here 4 users, that's why there are 4 time slots in a frame. This is a frame. Next, it repeats. Next, so next time slots is given to the user 1. He will transmit another symbol A. Next, so here for the user 2 there is nothing to transmit, so it is left vacant. User 3 also nothing to transmit, left vacant. User 4 has got something to transmit, he will transmit. So here these 2 time slots are empty. Okay, so here bandwidth goes wasted. It is go wasted. Okay, so we are not using our channel to the full capacity because we are keeping it empty. We are keeping the channel empty for a while because so this user 2, user 3 doesn't have any. They do not have anything to transmit, but still we have allocated time. We have allocated time slot, isn't it? So even though user 2 and user 3 has nothing to transmit, but we have allocated time slot. So here time slot is fixed. For every user, we have a fixed time slot. So if the user have nothing to transmit, that time slot will be wasted, or we are wasting the bandwidth, or we are not using the channel to the full capacity. Okay. Now, so to overcome that, anyway, so this is a demultiplexing, very, very simple. So to overcome that, we go for asynchronous TDM where we don't allocate any time slot to any user. Okay, we don't allocate any fixed time slot to any user. So we give importance to user who has something to transmit. Suppose you have something to transmit, you can transmit. Okay. So what happens here is, so user 1 has got something to transmit, will transmit A. User 2 has got something to transmit, he will transmit. User 3 has got something to transmit, he will transmit. Next, user D, user 4. Next, user 1 has got A. So user 2, user 3, they don't have anything to transmit, so we leave them. So next we give a chance to user 4 because he has something to transmit, so we'll let him to transmit. Okay. So by doing so, we are avoiding the wastage of the time slots, or we are using the bandwidth to its full capacity. But here in a frame there are only 3 time slots. Okay. So in this asynchronous TDM, so the number of time slots in a frame will be less than the number of users generally. Okay. So the number of time slots in a frame will be less than the number of users in a asynchronous TDM. But whereas in synchronous TDM, the number of time slots in a frame will be exactly equal to the number of users, or the number of multiple users we have. Okay. So this is about time division multiplexing. Now, so these are some examples. So we'll try to solve some problems in the next class. This is about most of the third unit generally. So in the third unit, so we should remember PCM, DPCM, delta modulation, TDM. So let me go back. So these are the things you must remember in third unit mostly. Sampling. This is a very, very big unit, length unit. So sampling, quantization, okay, and encoding. Encoding, anyway, you know how to encode. Next, you should remember PCM, PAM, delta modulation, DPCM, and time division multiplexing. So these are the important topics of the third unit. Anyway, we have something in the third unit also. So I hope you are okay with that syllabus. So let me start another topic in the same third unit, that is called signal space analysis. Here, so what is that? Okay. Now, so here we'll try to study the signal space of the communication system. Signal space in the sense geometric space. Now here we have a source which emits a symbols mi, m1, m2, m3, so on so on. It emits some symbols at every TB seconds. Okay. So we have transmitter. In the transmitter, so those symbols will be modulated. Okay. So they will be transmitted. We have a channel and we have a receiver. The receiver will receive x of t. What is x of t actually? It is a corrupted version of SI of t. Okay. Now here, so we have m cap or m hat. So that is what we are estimating. Okay. Now, so mi is what is being transmitted. The transmitting symbol mi. Now what is being received? M hat. It is estimation. Correct. So if both are same, it is called error-free transmission. Obviously, so the symbol that you have received is same as the symbol is transmitted. If the symbol is that you have received, it will be same as symbol that is being transmitted. Obviously, there is no error, right? So we call it as a error-free transmission. If they are not same, we say that there is error. Okay. So here we can only do some mathematical calculation to estimate the mi. We have to estimate, we have to guess what might have been transmitted. Okay. Now, so here we know all these blocks already, but we study in the pure mathematical way. Okay. So here, so this is the basic for understanding the digital modulation techniques. Okay. So we have studied analog modulation techniques. What are we have studied? Amplitude modulation. In amplitude modulation, we studied SSB, BSB, DSBSC, and we have studied frequency modulation. We have studied phase modulation. Okay, so on so. Now, so next we have to study digital modulation techniques. For that, we need this basic understanding of what? Signal space. So without the understanding or without the knowledge of signal space, you cannot understand the digital modulation techniques. Okay. Now, so here we always go with a probabilistic model. It depends upon probability or PDF. Okay. So here we are estimating. So estimating it depends upon probability. So what the probability of symbol M1 or what is the probability of symbol M2, so on so on. What is the channel noise, because it is also random in nature. So everything is in a probabilistic manner. So that's why we do estimation. At the receiver side, we have to estimate the transmitted symbol. So if our estimation is correct, so there is no error. It is called error-free transmission. If our estimation is wrong, so there may be error. So that is called erroneous transmission. Okay. Now, so I will start briefly today. So message source emits one symbol every t seconds. So here this source is emitting or it is giving one symbol for each and every t seconds. At each and every regular interval of t seconds, we get a symbol, new symbol. The symbol can be anything. M1, M2, so on, so on. We call it as M1, M2, so on, so on, so on. So let us take, it is emitting M symbols denoted by M1, M2, so on, so on, MM. So at each and every t seconds, we are getting a new symbol, namely M1, M2, M3, so on, so on, MM. Okay. Now, it is customary to assume that all the symbols that are being emitted are equally likely, which means, so the source is emitting symbols every t seconds, and it is customary to assume that all those emitted symbols are equally likely, which means the probability of emitting symbol M1 is same as symbol M2, so on, so on, same as symbol MM. So that is probability equal to 1 by M. You know this concept already. Okay. So if all are equiprobable, obviously, so the probability of each and every event will be 1 by the number of events. So here the source is emitting M symbols. So if all symbols are equally likely or equiprobable, so the probability of each and every symbol is same as 1 by number of symbols, that is M. Okay. Now, so here, so the source is emitting some symbols with equal probability, and those symbols need to be transmitted. So in the transmitter we do modulation. Okay. Anyway, so we don't talk modulation at this point of time, but so let us something like that. So MI is something symbol, SI of t is a transmitted signal. So that is suitable over a transmission, suitable for transmission over a channel. Now, so we cannot transmit M1 symbol directly. Okay. So we need to make them as suitable for a transmission over a channel. So that will be done by transmitter. So if we give MI, the transmitter will produce SI of t, corresponding SI of t. So that SI of t is suitable for transmission over a channel. So we can do transmission. Okay. Now, so here, so the signal SI of t occupies full duration of time t allotted to symbol M1, MI. So it is a energy signal. Please remember. Okay. So here the simple logic is, from the source we are getting a symbol. The symbol will be modified to SI MI. The symbol is MI. That will be modified to SI of t by transmitter. So the transmitter will modify that symbol MI as SI of t. Okay. Now SI of t is nothing but it is an energy signal. Why it is energy signal? Because so if something is time bounded, they are all energy signals. Why it is time bounded? As I told you, SI of t is defined. Oh, where I written? It occupies only a time duration of t seconds, or it is defined only during t seconds, or t, time capital T. So here it is time bounded. So if any signal is time bounded, it is tend to become energy signal. Okay. Now EI is the energy of SI of t. Obviously, you know how to find energy of any signal. Integration 0 to t SI of t whole square dt. So why integration 0 to t? Because it occupies only 0 to t. SI of t occupies only from 0 to t. What is 0 to t? It is a symbol duration. Why it is symbol duration? Because the source is emitting a new symbol at each and every t seconds. So after each and every t, time capital T, we are getting a new symbol from the source. So that's why SI of t also occupies over a duration of t seconds. Now, so we are transmitting SIFT over a channel which is obviously will add some noise. Okay. So obviously this channel will add some noise to the signal that we want to transmit. Correct. So there is a addition of channel noise. Okay. So obviously we always take the channel to be AWGN channel having zero mean. So what do you receive? X of t. What do you receive? X of t. But X of t is not exactly SI of t. So X of t is the transmitted signal SI of t plus some noise that is added in the channel. Now finally, what you receive is the transmitted signal SI of t plus some noise W of t. So you must write these things each and every time because SI of t is strictly defined from 0 to t only. It is not defined over entire time duration. SI of t is defined only for 0 to t. Okay. W of t is the channel noise. AWGN channel noise. Here, so now, so average probability of symbol error. Okay. So can you think of what is error first of all? What is the probability of getting error? So we'll talk about this later. So it is not correct to discuss at this point of time. So but just remember this formula. Just try to understand this formula. Okay. So I'll explain this a little bit later. Now, so here geometric representation of signal. So I told you already. So we need to represent these signals and noise geometrically. So geometrically means generally maybe 2-dimensional or 3-dimensional space. Okay. Now, now here, so here the transmitter is producing some signals S1 of t, S2 of t, S3 of t, so on, so on, Sm of t. It is producing M signals. What kind of signal? Energy signals. Okay. So this transmitter is producing M energy signals. Okay. Now, so to represent those set of M energy signals Si of t as a linear combination of n orthonormal basis function. So this is you need to understand very carefully. So this is algorithm. Okay, you don't worry about this. I am explaining algorithm. Okay. Now here, so we wish to represent everything geometrically. Here, so anyway, this is only symbols, number of symbols. Now this transmitter is producing S1 of t, S2 of t, S3 of t, so on, Sm of t, M energy signals. We need to represent them geometrically. How it is possible? Now, so to represent them geometrically, we need to have this algorithm. Okay, try to understand this very carefully. Now, so here I want to represent those set of M energy signals as a linear combination of n orthonormal basis functions. Okay. Now you must try to understand this very carefully. So what do you mean by linear combination? Suppose if I say y equal to a1 x plus a2 x2 plus a3 x3 so on, that is called linear combination. Okay. Now here how I am representing? I want to represent each and every Si of t as a linear combination of what functions? Basis functions. Okay. Now, so here this summation j equal to 1 to n Sij phi j of t. Okay. Now here, so what is Si of t? You try to understand this. Si of t equal to expand this summation. Always see Si of t is always defined over a duration of t seconds only. Okay. Now if you expand this summation, what do you get? Si1 phi 1 of t plus Si2 phi 2 of t plus so on Sin phi of t. I varies from 1 to m. Suppose if I equal to 1. Okay. What is I equal to 1 to m? They are here. S1, S2, S3, so on, Sm. I varies from 1 to m. You do one thing. Suppose if I equal to 1. What happens? Substitute I equal to 1 here. S1 of t equal to S11 phi1 of t plus S12 phi2 of t so on plus so on S1n phi n of t. Here S1 of t, an energy signal, is written as linear combination means what? So here suppose y equal to, generally we write a1 x1 plus a2 x2 plus a3 x3. This is what linear combination. Here what do we say? Y is a linear combination of x1, x2, x3, whereas a1, a2, a3 are some constant. In the same way, S1 of t is a linear combination of phi1 of t, phi2 of t, so on phi n of t. What they are called? They are called n. N is the number of those signals. They are called orthonormal basis functions. Okay, I will tell you what is orthonormal means. You might have known what is orthogonal. Orthogonal means perpendicular. So what do you mean by orthonormal? Okay, anyway, so here I am representing each and every SI of t as a linear combination of n number of basis functions. So here S11, S12, so on S1 are some constant. They are called coefficients of expansion. Okay, how they are defined? They define like this. Okay, so these are all simple mathematics only, so nothing to worry. So this is the Sij. This is Si. This is something like, in the Fourier transform we have analysis equation, synthetic equation. No? In the same way we have these two things. You must know these things very, very carefully. You must know these two equations. What is Si of t equal to? That equal to summation ij equal to 1 to n Sij phi j of t. This is the given constraint. And what is Sij? They are coefficients of expansion. They are something like constants. So how to find them? Integration 0 to t Si of t phi j of dt. So here there is a trick to remember Sij. So integration 0 to t Sij means Si of t phi j of t dt. So I varies from 1 to m, j varies from 1 to n, but m will be always greater than or equal to n. What is m? Number of energy signals. What is capital M? The number of energy signals that are being produced by the transmitter. What is capital N? The number of basis function that we are using to represent those m number of energy signals as a linear combination. Okay. So you try to understand this very, very carefully. So these two equations are very, very important. So you must remember these two equations compulsorily. No need to remember, just remember the basic definition. So we want to represent m number of energy signals as a linear combination of n number of basis functions. So how the basis function should be? Orthonormal. I will tell you what do you mean by orthonormal. So here this is a linear expressing anything as a linear combination of so many signals. Now the real valued basis functions are orthonormal. Okay, so we want to represent S1 of t, S2 of t, so on Sm of t as a linear combination of phi1 of t, phi2 of t, so on phi n of t basis functions. Okay, now the basis functions need to be orthonormal. What do you mean by orthonormal? Orthonormal means it has to be orthogonal plus it has to have unit energy. So if any signal, otherwise if any set of signals, if any two signals which are orthogonal to each other, at the same time they should have a unit energy, then they are said to be orthonormal. Means, so if two signals are perpendicular to each other and along with that they have unit energies, they are said to be orthonormal. So orthogonal plus unit energy gives you orthonormality. Okay, here, so what do you mean by orthogonality? Means perpendicular. So perpendicular means this is what orthogonality. So if we integrate 0 to t phi I of t phi j of t dt equal to 0 if I is not equal to j, 1 if I equal to j. Okay. Now, so this is simply a definition of orthonormality. Okay. So let me explain this. Suppose if I equal to j, both are same, means both are same, both signals are same, then what happens? Integration 0 to t phi I of t phi I of t dt equal to integration 0 to t phi I of t whole square dt equal to phi j of t whole square dt equal to 1. Means what? Unit energy. If I equal to j, so both are same, then if I equal to j, so this equal to 1. If I equal to j, this integration is equal to 1. But what does this integration mean? This integration means this means it has got unit energy. Suppose if I is not equal to j, what do you mean by that? 0 to integration 0 to t phi I of t phi j of t equal to 0 means this defines orthogonality, means perpendicular. Okay, so this definition is for orthonormality. Okay, so anyway, so we stop here. So you try to understand this very carefully, right?